So methane gas, what is it? Where does it come from? And why is it important? Well, methane gas is a gas that's found in our atmosphere. Now, remember, atmosphere is the layer of gases that surround the Earth. And there are the six major gases found in our atmosphere. And the first one is nitrogen. Nitrogen makes up 78% of our atmosphere. So when you're breathing in air, 78% of that is nitrogen. About 21% is oxygen gas. Argon, surprisingly, makes up 1%. And then we get down to the much lower numbers. We've got water that takes up on average about 4%. Of course, there's a higher concentration of water over the oceans and watery parts of the planet and less over the drier parts. We have carbon dioxide, okay, that is released from burning fuel and from people respiring, animals respiring, plants respiring. And we have methane. Now, carbon dioxide is 0.04% and methane is 0.002%. Now, the last three of these are all greenhouse gases. And water is a natural greenhouse gas, and it's usually not talked about because people don't really change the concentration of water in the atmosphere. That's mostly determined by the oceans. Carbon dioxide and methane, though, are anthropogenically altered, or the activities that humans carry out can alter the concentration of these greenhouse gases in the atmosphere. Now, methane at the moment, the 0.002% is actually 1.9 parts per million. If you had if you had a million parts of particles of the atmosphere, you would find about 2 of them in every million were methane. Now, the methane concentration is actually at flux. That is, that every year it will there'll be some methane released into the atmosphere, and there'll be some methane taken away from the atmosphere. And actually, in the atmosphere at the moment, if we would take all of the atmosphere surrounding the Earth, there are 5,400 teragrams of methane in the atmosphere. Well, that's about 5,400 million tons of methane in the atmosphere. Now, every year, 580 teragrams of methane is released to the atmosphere every year from different systems. And in fact, there is 560 teragrams of methane removed from the atmosphere through natural processes. That leaves a wee imbalance here of 18 to 20 teragrams of methane that is added to the total amount of methane every year. And that's what's really the problem when people talk about methane emissions when they emanate from agriculture or from other places, is that they will be contributing to the total amount of increase in methane. Now, over the last 41 years, the National Oceanic and Atmospheric Administration of the United States of America has measured the methane concentration in the atmosphere. And what we can see is that the methane concentration has increased over time. And in fact, if we go before the industrial age, the actual increase in methane is about 2.5 times. So it's 2.5 times larger than it would have been, let's say, 300 years ago. Okay, that's quite a lot. But where does it all come from? So we've got three broad areas that methane comes from to go into our atmosphere. The first one is called biogenic emission. Now, biogenic emission is methane that is released into the atmosphere from biological sources, and that can be from the stomachs of cows through to the bottom of a pond. So anything that comes from a biological source is biogenic emission, and that's about 65% of the methane that is released into the atmosphere every year. Now, we then have this other type that is called thermogenic emission. Now, thermogenic emission is from methane that has been produced from heat and pressure beneath the Earth. And it comes out when we explore for coal, gas, and oil, fossil fuels. Now, how do we know that this 30% is thermogenic? Well, interestingly, is the methane that comes from beneath the Earth is actually quite dated. It's been sitting there for a long time. So what we can do is we can carry out carbon-14 dating. So when we take a sample of the atmosphere and we carbon date the methane in the atmosphere, we find that about 30% of it has not come from biological material that's been about in the last 10 years. It's come about from millions of years ago. So we know that this methane must have come from non-biological sources and from this thermogenic emission. Now, the last one that we have is pyrogenic emission. Now, this usually comes from biological sources, but not natural processes that emit them, but from fires. So if you take biological material and you set it on fire, then some of the gases that are given off when the fire happens are methane, and that accounts for about 6% of the emission. So we've got three major sources here: biogenic, thermogenic, and pyrogenic. So we've said about 580 teragrams of methane is released into the atmosphere every year. But where exactly does it come from? Well, when we know that 60%, 65% come from biogenic, but where specifically? So the methane emissions by source have been measured, and the way that they've measured this is they've gone and taken a satellite called the Copernicus Sentinel-5, and as it goes across the Earth, it measures where methane is emerging from the Earth. And then it looks about what type of activity is happening there, and it allocates it to the methane from there to that type of activity. Now, this is called top-down accounting for methane. And from this, we get the following types of areas where methane is released from. So fossil fuel production and use. So remember, that's coal, oil, natural gas production. That's about 111 teragrams per year come from that. We have agriculture and waste. So that's anything from rice paddies, actually produce a lot of methane, to farming cows or dairy, or just taking the effluent, the product that comes from animals and from people, that's the waste, that produces 217 teragrams per year. Okay, now that is a biogenic source, and remember the first one was a thermogenic source. So that produces quite a lot of the methane. We have biomass burning, which is this pyrogenic source, and it produces about 30 teragrams per year. The next source that we have are wetlands. Now, wetlands are environments, mostly freshwater environments that are covered by water, and those are found in the natural environment. So natural wetlands produce about 181 teragrams per year. Now, some sources say wetlands produce about 30% of it, and some say they produce up to 50% of the methane every year. But from this top-down approach, they've measured about 181. Now, the last source that we have for producing methane are other emissions. Now, these other emissions can come from wild animals, so we can have wild bison or wild buffalo or camels, or they can also come from termites. Termites produce methane as well, so termite hills. So that is the last 37%, and these produce the 580 teragrams per year of methane that is released in the Earth. Into the atmosphere from the Earth. Okay, so but how do these biological processes happening? So I'm not interested at the moment in the fossil fuel production or the burning, but I want to look at these green arrows. What are the different ways that methane are produced from biological sources? Okay, so the two major places that we'll look for methane is going to be from biological methane emission are going to be in ruminants, that is in the stomachs of cows, camels, horses, and in wetlands. They are major places where we have biogenic methane emission happening. Now, what happens in these places is there are microscopic bacteria and fungi that carry out processes that produce methane. They need plant matter. Okay, so they need the matter from plant material. They need an anaerobic environment. That means an environment without oxygen. Okay, so these processes can happen, and they need a moist environment or environment with water. Now, of course, in a cow's stomach, let's give as an example, there are all of these four things happening. There is specific bacteria in there. There are plant matter that they have consumed. There's no oxygen in there, and there is water in there, so it will have all the conditions. And at the bottom of a floodplain or a pond or a lake, we can also have the bacteria living there in a non-oxygen environment, plant matter that has been washed down from the hills above, and of course it's moist. Also, Remember, biogenic, we can have some termites. The actual other place that we have quite a lot of biogenic methane emission is organic waste. So the waste that comes from cities and towns or from dairy farms, the poop that comes from there. Okay, so let's look specifically at the processes on how these happen. So we're thinking about at the bottom of a wetland or in the stomach of a ruminant. So the first thing that happens is the hydrolysis of cellulose. Now cellulose is a long chain of carbons, oxygens, and hydrogens. Now the cellulose is actually, here it is here, a long chain of it. It's called a polymer because it is a repeating unit of sugar. Okay, so there are repeating units. Here it's of glucose, so they can be hundreds to thousands of units, and cellulose is actually found in plant matter. So if you were to look in the leaves and the trunks of a plant, you would find the polymer cellulose. Cellulose is what holds the structure of plants together. Now, when people eat cellulose, when you eat plants with high roughage, let's say you're eating some celery, then you can't break down all of the energy that's in there because our stomachs don't break down the cellulose. However, the ruminant stomachs, the cow stomach, can break down the material that's found in plants, the roughage, and so can these anaerobic environments at the bottom of these freshwater lakes or swamps or floodplains. Now, so what happens is this cellulose molecule actually sits in these environments, anaerobic environments, and undergoes a process called hydrolysis. Now, hydrolysis, what it does is it breaks the cellulose into smaller units, and in this case, smaller glucose units. Now, that's important because actually the cow's stomach can't absorb the cellulose as energy, but it can absorb the glucose into the bloodstream and do something with it. So that's the first step. The second step that happens in these environments, and remember they could be in rice paddies, they could be in the stomachs of cows, is you have glucose fermentation, or anaerobic because there's no oxygen glucose fermentation. So you have the glucose unit, okay, so 6 carbons, 6 oxygens, and 12 hydrogens. So you have this unit and some water in the environment, and what happens is with an enzyme that's in there that's produced by the bacteria or the fungi that's in there, it breaks it down into smaller molecules. Now the two molecules that we're interested in here, well, there's this one called acetate or ethanoic acid, but it's often in the acetate form. So it breaks into acetate here, it breaks into carbon dioxide, and also produces some hydrogen gas. So at the bottom of a swamp here, you've got this acetate being made, this carbon dioxide and this hydrogen gas, these wee gases that might bubble through here, and this acetate. Now this acetate is really important for the next process. Okay, so no methane is being produced first. We've had two processes. The first one was to break down cellulose, and then the second process that is happening is we are breaking the glucose into smaller units. Now, of course, if this was a cow's stomach as well, we have the different stomachs of a cow or a ruminant that can carry out these different processes. Okay, so let's say that we have this acetate here. This acetate can undergo an acetoclastic methane. It can produce acetoclastic methane, and it can do this through another fermentation process. Now what happens is the enzymes that are found in the bacteria, here is the methyl coenzyme M reductase, can be found in a bacteria. It will break this down and produce a methane molecule, a carbon dioxide molecule, or a methane and carbon dioxide molecule. And this is what can happen in a cow's stomach. It can happen at the bottom of a swamp. So when a cow now has this gas building up in its stomach, it can either burp, comes out its mouth, or it can fart and it comes out the back end, and you get this methane and carbon dioxide coming out, produced from this biological source. Of course, if the cow hadn't eaten this grass, the grass could have washed down to the bottom of the wetland and it could have gone through the same process. So there's another way that we can also produce methane. So remember in the previous slide, we had acetate, carbon dioxide, and hydrogen. So if this carbon dioxide and hydrogen is sitting at the bottom of a wetland, it can actually go through a hydrogenotropic methane, produce that method, and it can take the carbon dioxide and the hydrogen, and it can undergo an oxidation reduction process with the help of an enzyme where they exchange electrons, okay, and we get methane produced and water produced. So this is I guess this hydrogenotropic methane production is about 1/3 of the natural methane that's produced, and the one we had on the previous slide was about 2/3 of the natural methane produced. So methane can be produced by... Okay, let's summarize what we've learned in this video. So there are 3 major processes or sources of methane in the atmosphere: biogenic sources, thermogenic sources, and pyrogenic sources. If we look at the biogenic source, we can see that there is a series of steps, processes that have to occur to produce methane. The first step is the hydrolysis of cellulose. So plant material needs to go into an environment that has specific type of bacteria and fungi. It has to be wet, it has to be in the absence of oxygen, and the first step is to undergo hydrolysis of cellulose. The second thing is the fermentation of the sugars that were part of the cellulose needs to happen in this environment, with the help of certain bacteria or fungi. And the third part here is that we have 2 different steps that we can use to produce methane. And the first step is called acetoclastic, and 2/3 of the biogenic methane is produced through this step. Remember, that's with the acetic acid, or the acetate is broken down into methane and carbon dioxide. And we had the second step, which is about 1/3, and the hydrogenotropic step usually only occurs in wetlands, where the acetoclastic occurs in both wetlands and in the ruminant animals. The hydrogenotropic step is the one which is about 1/3 of the methane. And what happens here, remember, is the carbon dioxide that has been produced by steps 1 and 2 and the hydrogen that was produced by steps 1 and 2 undergo an oxidation reduction process where they swap electrons and they become methane and water. And that's where methane comes from. So if you know where the sources where methane comes from, and you know that we are producing 580 teragrams of methane every year, with 20 more teragrams more methane than we need, you can see that we need a reduction of about 0.3%. But where do we take the methane from? Where is the best place to remove methane from these 3 different sources from what you know now? I'll leave that with you.